Hello everyone, my name is Louis, and in this video I will show you how to use the last software in our toolchain, so the CoreComparison software, together with the RingIndicator software to cross-date your course. So let's have a look what we have. Here I have a bunch of cores which are indicated, and I now want to cross-date them. Good, and see if I made any mistakes, did I forget any rings, or should I add some missing rings, these kinds of things. So what we will do, first we will open our two cores, 1 and 2. So I just clicked on RingIndicator twice, so it will open two instances. I will open the two cores, number 1 and number 2. Okay. Okay, so my cores are now both open, and now I want to check if they are cross-dating well. So these are two cores from the same tree, so their ring width pattern should be very similar. So I open the CoreComparison software, I say txts, and then I go to my folder, and I say which ones I want to compare. So now I'm only going to compare 2 from the same tree, but you can open 50 or whatever at the same time. So I'm going to do it like this, open. Okay. Click this away. Okay, so now we have the ring width curves of both next to each other. And I can already see, so here is the gleichläufigkeit and the correlation shown between all the cores. So now it's only 2, so there's only 1 square, but if there are multiple, then you have a bunch of squares which compare all of them. And so here I see that the gleichläufigkeit is very low, so 0.3 or 0.4, so probably there is some kind of mistake. And if I zoom in, I can already very quickly see that like the valleys and the peaks, here again, the valley, it's shifted 1. So probably in one of the two I have either forgotten to indicate a ring, or I have indicated a ring too much. So let's have a look. It probably happened quite early on. So I will open my 2 cores. So it probably happened quite close to the bark. So I will have a little look. Here I see nothing wrong. And here, yes, okay, I have found it. So here there is a small mistake. Here there is a ring that shouldn't have been indicated, that shouldn't have been a ring. So I can remove it. This one is a little bit, yep. I can save it. So Control Save or Save. And when I now go back to the CoreComparison and say refresh, bam, okay, gleichläufigkeit is way better and the correlation is way better. And now we can check again, does it run correctly? And we can see, as the peaks and the valleys nicely aligned, we probably have a well-indicated core. So now I have shown this with just 2 normal cores, but you can also load in a reference chronology underneath, and that's what I will show you now. So to build a reference chronology, well, to put in a reference chronology, we have to create a txt file like this, a ring width txt file which shows the chronology. Okay, and I have built a little R script that does this. So it starts from an Excel file, okay, or whatever you want to start with, because it's all in R. So, but here I've implemented it from an Excel file. So in the first column you have the year, and in the second column you have like the standard deviation. So your ring width index. Okay, and then when I open this file. Okay, so when I open this file, we have here the script. So first remove everything and read Excel, and then run it, which first reads the chronology Excel, then builds a table in like the correct format, and then exports it all in write table. Okay, and so when it has exported it like this here, we now have this one. So the AA Gron ring width, and I can copy this into my folder with my course. So over here, I can copy it, and I gave it like the AA name, so it's nicely on top, then it's easily identifiable. And then when I would launch CoreComparison, yes, okay, I can now say, okay, I want the chronology, and I also want my two files, these two cores, open, okay, and now I have all of them here. So I see that my two cores here have a very good gleichläufigkeit, but not with the chronology. That's because this chronology is just not from the same site. It was just a random chronology that I had laying around, but it's just to show the functionality. Also, this has like very high valleys and peaks, the chronology here. That's because this site has much wider tree rings than the one that we're looking at here. You can change that by just in the R. You can change the size of these valleys and peaks in this R file by changing this parameter here. So change the 3000 to have higher valleys or peaks. That's just like the size of the ring width you have there. You can change it to like 1000, and then the valleys and peaks will be smaller. Okay. Good. Save. So that's this. You can also like zoom and look around. So for now, the functionality of this software is very basic. So it's only looking at ring widths, and comparing with the chronology and seeing what the correlations are, which is like fine for most like error checking, certainly in living trees or in already cross-dated samples. But in the future, we will add quite some functionality to also like more automatically make these chronologies from whatever is loaded and like find errors and shift within here. And so this is stuff that is coming but is not made yet. Okay. Once everything is cross-dated, then we want to load everything into R and actually start doing stuff with our data, both our ring width data and our density data. And so for that, I have built a function, the XCT read function, which you can also find on GitHub. So the previous function, what was it? The XCT cron, so the chronology to put inside CoreComparison, that's also on the GitHub. And this one, the XCT read, has its own separate GitHub, which is linked on our site. So the XCT read is a function. I will again open R. Okay. So the XCT read function is shown here. It is a function that reads all of these txt data. So this is a data folder in which I have put a whole bunch of txt files from the indications. Yeah, just as an example. So a whole bunch of indication files, and this function can read everything inside these txts and then calculate all kinds of things from it. Okay, so I have here an example that is also on GitHub on how to use it. So first we need to load some packages, mainly the tidyverse, and I also load a DPLR here because the output of our function, the XCT read function, is in the format of DPLR. So in the DPLR format, so you can easily start detrending and making chronologies and whatnot. You don't have to do it in the DPLR. There's also like an option to just do it in long format, but that's an option. Okay, then we need to load the XCT read function, and then I define my data folder, and then here I show a whole bunch of options that you can do with this function. So the easiest thing to do is just read the ring width data. So everything is loaded, yes, and I will now just read this, the ring width, and when I go to ring width, then here I have a DPLR formatted ring width file. Okay, very easy. Then this software was, this toolchain is mainly made for density measurements, of course. So all these other things are examples of what to do with density. So for example, you can say here the output I want density. So in the previous one the output was ring width. So now I want to look at density. So I give my path. I say I want to look at density, and the density type is a fraction. So you have two types of density parameters that you can calculate, either a fraction or a fixed width. So what do I mean by fraction? So for example, you want to have the mean density in the last 25% of your ring. So you define your late width by being the last 25%, for example. Then you say, okay, I want the fraction, and within that fraction, I define that fraction as the area from 0.75 to 1, so the last 25% here. You can also say the middle 25% or whatever. You just say here the beginning and the end. If you want to have the density of the whole ring, you can just say 0 or 1, or only the beginning, so 0 and 0.5. So yeah, you indicate it here. And then you give along the function, so I want to have the mean within that area. You can also say median or many other things, which are all explained here. There are many different options. Okay, so if I do that, if I calculate my density, up, like this, now I have density here, and this is a DPLR formatted density file. So in 1980, my L772 had a density in the last quarter, an average density of 666 kilograms per cubic meter. Okay, so that's like the basic one. Then let's see. So yeah, that's the end. That's if you want to have like the middle 50%. Then the other type, so you have the fraction. So each time you take a certain fraction of the ring, independent of how wide it is, but you can also make it fixed. So I want to look at the last 100 micrometers of the ring, of each ring. So it doesn't matter how wide it is, I only want to look at the last 100 micrometers or 200 micrometers or whatever. That you can say by saying density type fixed. I want to say at the end, so the last 100 micrometers. You can also say at the beginning, that's by here defining, that's by saying start. So you have start and you have end, but here we're going to go for start, for end. So the last 100 rings, the 100 micrometers, which is a common thing for example, to calculate MXT. And again, the mean. There are many different functions, mean, median, again, so the same. Then I also implemented a special function. So instead of mean and median, I also implemented the mean top x function, which is just within, for example, here I define within the last 300 micrometers of each ring, I want to have the mean of the top 20%. So here the x is like the percentage, so 0.2 is 20%. So the mean density in the of the 20% highest values in the last 300 micrometers of each ring. This is like a kind of a convoluted way to more accurately calculate MXDs, and you can experiment around and see which parameter fits best. Okay. There is also an option to like remove super narrow rings. So for example, if you really have like a few rings which are only a few cells wide and density calculations there are not very useful, then you can have like a filter here which has like a minimum ring width of, for example, 3 millimeters. That's maybe a bit wide, but whatever. Okay, so these are all in DPLR format. A different way to export it is ring width density, and so this will be in long format. So I will maybe show that here. Okay, so the previous one was density and ring width, so separate in the DPLR format. But if we now go to data, so the other one that I did, so data, the new one with ring width density, that's a long format data frame which has the sample, so the sample, what year it is, the density, and the ring width. So this is actually a more standardized way to view and load data into R, but it doesn't come along with it doesn't go along with DPLR easily. But in this way, you have both options. Okay, good. This. And then a last thing that you can export is just the raw density profiles. So instead of like having the average in the last 25% of your ring, now I just have the profile in each ring. So I can do it like this, hub, data. And if I now go to data, then you have the sample, what year it is, and then the pixel number along that ring. So the first pixel in 76 of this sample is this density. And this way you just have the whole density profile within each ring. And I also implemented here the row number along the sample so you can keep track of that. And so you see after each year we have here the end of 1977, and then it goes to 1978, and it's again pixel along the ring number 1. Okay. And this way you can also do all kinds of calculations on the actual density profiles without having to use our own functionality. Okay, good. That was all, I think. Okay, thank you.